Okay. All right, so last I checked, which was just a couple minutes ago, there were 5 of you who have taken the test. So we're still inside, it's not technically due until today. But as always, try to get yourself caught up. I'm about to dive into a new unit. Now, I also decided that we're just going to continue taking our exams on our laptop. Got them all there. That's how we proceeded. If we had been in the classroom, I would love to give my own exams, but we'll stick with what we've been doing. Okay, so I don't look right now. At least for the next exam will just be, you'll take it home like you've taken all the others. So it won't be an in class. Still working out final exam. Now the final exam itself probably will just be the last material we covered. We'll see. I'm not sure yet. So any general questions? I did bring, so this was where I keep my list of names. So I think you emailed.
I completely forgot, yeah.
But did you email me a list of names?
No.
Okay.
I
You can still take care of it today. Like I
Okay.
say, it's
Oh,
right after
yeah, I
class.
just completely forgot.
Yep, just right after class, we'll get you in. So it's a
Okay.
little easier here because you can see who's been taken already. All right. So I'm just gonna do a head count of 2, 3, 4, 8, 9, 10. All right, I'm gonna go
Michaela,
Michaela,
Yes.
Clark,
Kelsey,
Kelsey,
John,
Jenna,
Adrian,
Adriana,
Catherine,
Adrian,
Anna,
Anna,
Catherine,
Catherine, William,
Anna.
Hannah. All right. So we're going to start in chapter 4. We'll go back and talk about historical enumeration later. What I want to spend a good bit of time is working on our own positional place value system, really beginning to develop an understanding of it. So here's a number. 5,678. Right. Now, do you know that we use base 10 as our base of our numeration system? Do you know what that means? To say we use base 10. So what's it mean?
Every 10 you start over.
Every 10 you start over, okay? I like that. All right. That is true. Back to the next digit. Now, here we have what we call base 10. We have 10 digits. 0 through what? 9. And that's not an accident. Turns out, whatever your base is, that's how many digits you have to make the system work. So, but there's a lot of hidden meaning going on in here. So what I'm going to do is write this number out as it actually is. One after writing one. Anything with 0 power is 1. Numerator. Anything to the 0 power is 1. So this is 1's place. That's why it's called 1's place. Basically 8 times 1. This is 10's place. 7 times 10 is 6, 7 times 10. 100's place. And then what? 1,000's place, and so on and so forth. Now, and this is referred to as expanded form. Remember after expanded form. But we could work in any base, as it turns out. And some other bases have actual practical use. Let's just see how it would work if I were in another base. Let's say I had. Two. I'm gonna write 7 in letters, spell out the word 7 down in the subscript. So when I see this, my understanding is this is no longer base 10, it is base 7. The only one that we don't write is 10. So that, and you will see sometimes they, within my math level problems, they'll write TEN here that they really should. If you don't see anything, you know it's base 10. Anything else, we write it. And why would we write it in letters? So we don't, what, if we try to put a digit there, we may end up what, making it part of the number thing it's base 10. All right. Now, first off, as I said before, if it's base 7, then I have to have only like 7 digits to make it work. And it would just be 0 through 6. If you go base 5, it would be 0 through 4. Base 3 would be 0, 1, and 2. Base 2, there's a real practical one. 0 and what? 1. That's it. It's all binary. And like in base 10, sometimes for this decimal. Octal would be base 8. Base 16, it's called hexadecimal. Base 2, base 16, both have computer application. You know, big time binary. It's what they originally used for coding and still do. So, first thing we're going to, and really the emphasis today is how do I take a number in another base and write it as its base 10 equivalent? And so, process, I'm going to show a couple ways to do it. First way is just to write it out in expanded form, just like I did here. And that's where you really see why it is base 7, no longer base 10. I'm going to have 4 times, not 10 cubed, but what? 7 cubed. And then down the line, plus 3 times 7 to the first, plus 5, 7 squared. Not bad. 5 times 7 to the first, plus 2, 0. And then all we got to do at that point is crunch the numbers. So,
Professor Cunningham,
yes, ma'am.
what were all the powers after 7 in that one?
Okay, so since it was 4 digits, you'll just start out at 7 to the third. And then next one will be 3 times 7 squared. And then plus 5 times 7 to the first. And then plus 5 times 7 to the 0.
Okay, thank you.
You're welcome. All right. So incident in class, you need calculator. We're going to do a lot of number crunching. So I would not expect that you're going to do all this mental here by that's just cruel and unusual. Now, if you have an 84, it gets a little easier because I literally can type that whole string in. If you're using your phone, which is more of a scientific calculator, you got to do it. You got to actually do it from 7 to the third, and then times what 4, and you find each one of those individually, and then add them up. Takes a little bit more time. So, but on an 84 or even on a TI 30, it says I literally, and I don't even have to put parentheses. I can just go 4 times 7 to the third plus the calculator will sort out the order of operations. 3 times 7 squared. And when I'm actually doing these rapid fire like this, I see 7 times 5, I just put what, plus 35. And then the last one, I don't put 2 times 7 to 0. That's really just 2 times 1. So I'm just going to put plus what? 2. 1,556. But it's really just do the arithmetic, crunch it out. and you have its base 10 equivalent. Okay with that? All right, now let's say you're using your phone. Anyone using your phone here? Okay, you got your phone.
Yeah.
All right, that works. All right. Or if you just have like a little scientific calculator, or even just like a little number cruncher that just works by, binary operations, that means 2 at a time. Can't put it all in there and hit enter like this. There's a pattern to this. I'm going to show you what's called the calculator shortcut. So it's really put together expressively for this kind of calculators, pre-graphic calculators like this. All right, so we'll come up with the same answer, but I'm just going to look here. I look at what the base is, which is what, 7. So when you and you can do this on the graphic calculator, follow along. So if you don't have an equal button, you got an enter. You have an equal button. So every time I do one operation, I'm going to hit equal, or I'm going to hit enter. So I'm going to start here. And I'm just going to use this calculator. And I'm going to go first digit here times the base. So 4 times 7, hit equal. Plus the next digit, hit equal. Times the base. Now you start to see the pattern. Plus the next digit, which is a 5. Times the base. And then plus, you always get to the last digit here, it's plus the 1s, plus 2. And then what did we get? Same thing, 1,556. That's referred to as the calculator shortcut. Okay. So on using that kind of calculator, it's very advantageous. Why in the world would that work? I'm going to take this expanding form. I wrote out 4 times 7 cubed plus 3 times 7 squared plus 5 times 7 to the first plus 2 times 7 to the 0. All right. And what I'm going to do, I'm going to put this in what I'm going to call, this was the expanded form. I'm going to write this in something I'm going to call nested form. What I'm going to do is basically factor out common factors of 7 until I can't anymore. And I got to keep everything grouped up. So when I look here now, there's literally no factors of 7. It's really 0 factors of 7. So don't have any there. But here, these 3 terms here, I have at least 1 factor of 7. So I'm going to factor it out and watch my grouping. So put a bracket here. So out of each one of these, I'm factoring 1 factor of 7. So that would leave me with 4 times 7 squared plus 3 times 7. Now here I factored that. Yes. Yes. Here I would be left with just what, plus 5, because I would factor out the lone factor of 7. We'll leave 1 there. We don't have to write it. Or I can even write it 5 times 7 is 0. But I'm just going to write at that point plus what? 5. Now, don't forget I have plus 2 on the outside. And, it's 2 times 1. So I'm now just going to write 2. Okay. Going to do the same thing. Factor out now common factor of 7 out of here. So that would lead me that way. 7 to the first. Now plus what? 3. I didn't factor anything out there, so I got plus 5. Plus 2. All right, I can't do anything more here. So I've gotta remember, okay, how does this work? I went 4 times the base to 7, right? Plus 3, and then times 7, then plus 5, and then times what? 7, and then plus 2. So order of operations says always work innermost what grouping symbol, right? That's where you start. That's here. Times 7, then plus what? Then times, then plus, then times 7. That's why it works. And it's just simple factoring, rewriting it in this. And you're gonna, then I, when you get to the homework problem, we're gonna ask you on a couple to do this. And how they, I want you to think through it, and we will certainly on Thursday, if somebody has a question. Which I figured you might, we'll work it. But we're gonna basically have to break one or a couple of them down like this. Okay, questions thus far? So what we've learned so far is basically how to take a number in another base and write it to what? Base 10. That we've only worked with one other base, and that is base what? 7. So let's work with a couple others. That's just about in my camera range. Let's see what you can do. Do base. Let's do this. Now, I'm gonna ask the question before I put a base here. What would be the smallest least base I can think of this? That could be 4. I can bigger. It has to be bigger than 5. It won't more than 5. 6. Okay, because there's a 5. So remember, yeah, that's why I asked the question. Just whatever your base is, you have to have that many digits, and it's 0 through, and it's always going to end up being what? 1 digit less than the base. So if you were base 5, you would have digits 0 through 4. If you were base 6, you would have digits 0 through what? 5. Now, certainly this could be bigger than base 6, but it couldn't be any smaller than base what? We'll do base 6. Does everyone understand that? All right, so what I want you to do, a couple things. I want you to write this out in expanded form. Right, now work it out. And then convert it to base 10. And I want you to do it by crunching out the expanded form, and then try the calculator shortcut. And see if you can get the same answer. All right. And go. So it's, if you, I don't know how well you guys can see on my video, but it's 3, 5, 4, 3, base 6. For those of you who are virtual, tuning in virtually. Reagan, can you hear me and see me okay?
Yeah, I can.
All right, good deal. All right. Good one, too. You don't have to write it down. So that's not bad practice either. Again, you're gonna. And there's gonna be a little variation on how they, still the same thing, I just don't like the order per se, but I want you to think through that. 855.
Yeah.
Okay. Well, no, start. It's 3.6. Okay. So this worked out to be 855. Standard form would have looked like 3 times 6 cubed. Squared. First. Plus 3 times 6 0. One's place. Which again, computing that out, 855. And actually, when I was just coming up with the answer, so I could get around and check, I used a shortcut. It was just a little quicker, but than punching all that in, believe it or not. Graphic calculator. Okay. Okay, so another thing about how you read. This we read is 5,678, and we read it that way simply because of those place values. So if you're working in another base, it's easy to do because you're so what? I mean, literally, you do not think about it. You would just say 5,678. You don't say 4,352 base 7. As soon as you are verbalizing it in that way, you're really thinking base 10. So when working in another base, you're literally going to go 4,352 base 7. That's it, right? In terms of just verbalizing the number. All right. Let's work with another base. Let's work with base 16. All right, that sounds crazy right off the bat, because how many digits would you need? 15. You need 15 digits, and we only know 10. We have 10 known digits we work with. So, and this is standard. I'm about to show you. This is how base 16 works. Since we need 16 digits in base 16. There's our 10 digits there. 0 through 9. Now we got 10. So what we do by convention to get our 6 more digits that we need for our 16 digits. Capital letters starting with that. And F. Now, and I do this day, especially when I'm having to do conversions. work day 16. I write this out, I just jot it down somewhere. And what is the equivalent to the digit A in day 16 if it was in day 10? 10. This is 11. This is 12. 13. 14. and what, 15. I have that translation. All right, so I'm gonna have you convert number of day 16. 4. 16. Convert that to base 10. See what you can do. And I will do the same. Now, when you're working this, obviously you're not going to punch what B. There is on 84, if you really wanted to do that, there is a way you can store numbers into letters. And but it's not practical. So, but you could do it. So when you actually do the computation, you're not going to punch B and you're going to punch what? 11. You're not going to punch C and you're going to punch 13. All right. So it looks like you have a number. Looks like you have a number. I could be wrong. I'm not wearing my glasses. I think I've got 19,399. All right. The 3 or 4 of us got it. All right. Yeah. Not sure. So if I could. Plus 11 times 16 squared. Then yeah, plus 12 times 16. Right here.
Is that
Now,
zero?
so you can do that, or you can do it. That's it. Okay. So make sure that. That was it. So just that last one. Did you get it? 19,399. Got it? How we do? Got it? Excellent. All right, so base 16 now, not today. They're going to be a few weeks down the road. That just looks awful. We're going to do some arithmetic in other bases down one, so that we learn. And eventually, you're going to teach arithmetic in base 10. Right? You can work in any base and understand why things work when we do the arithmetic. Then you have a much deeper base of knowledge. So here's a problem for you. What this notation means is that's base 16 under that's base. Now we're not doing this today. Pretty good. But how and why are we supposed to do that?
Convert them both vendors.
You can. That is absolutely a problem method solution. And when we do the arithmetic, that's how I'm going to do it. Start it. We'll actually convert this to base 10, convert this to base 10. Do the arithmetic, and then convert the answer back to base 16. Then we're going to say, could there be a quicker way? And then we'll look for a quicker way. So the issue is we have to, we cannot think how could we do it directly? We would have to know all the products of what base 16. What is one of the most traumatizing things for students when they're in about the 3rd grade? Learning their what? Multiplication tables, rote memorization, flashcards, saying little sayings. 8 times 8 fell on the floor, picked it up, it was 64. Stuff like that. So, all right. Well, the other thing we want to make sure we tackle today is because we've got a pretty good handle on how to take a number in another base, convert it back to base 10. What if we take a number in base 10 and want to convert it to some other base? That is, go the other direction. That's what we want to look at now. And let's take one we know. So we can definitely include this one. We'll write it on the side, just have reference. 3, 5, 4, 3, base 6, we converted base 10, we got 859. All right, I'm going to show 2 ways on this as well. The first way is not practical. It just shows you why it makes sense, why things will work. And then we're going to look at a more efficient method. So use this first one. If you don't want to write it down, you don't have to. But so the problem's going to be 855 2 base 6. So I'm going to do this 2 ways. First way, no, we just convert 855, which is in base 10. So we worked it. We started here and got 855. So on this, what we're going to learn now is process to take a number in base 10 and go to some other base. And so the first one we're doing is one that we already know the answer to before we ever get started. We know what this is going to be in base 6. There, we'll look at that. But what is method? So again, I'm going to show 2 ways on this. This first way is you're basically going to again getting back to our position in place value system. The second way I'm going to show you is going to be more efficient. But if I were doing this, I would have to just thinking it out, I've got to figure out how many times that is, or what is the highest power, since I want to convert to base 6, can be divided into 855. Now, it doesn't have to divide evenly. That just means that 6 to this power is less than what, 855. I got to first figure out, so I grab my calculator. I might try 6 to the 4th. And I get 1,296. So I know I'm not going to have that, what, place value of 6 to the 4th. Can't. When I try 6 cubed, however, it's 216. So I know that's going to be the biggest one. And now what I want to do, I'm going to do it up on my calculator. If you ever had trouble with remainders of division using a calculator, you will no longer, after we're done with this, be able to find any remainder at any time. I'm going to take 855 and divide it by 216. Now that is again what, 6 to the what, 30. Now when you do division on a calculator, that decimal part that you see, one that tells you didn't divide evenly, right? That decimal part is not the remainder of the division. It is the decimal form of a fraction that is remainder over divided. We're dividing by 6. And so it's got that top, it's got to either be 0, 1, 2, 3, 4, or what? 5. I'm taking 855. Dividing it by what? 6 to the 3rd. Now, I need to know 2 things. I need to know how many times it goes. That's the easy part. That's on the left of the decimal point. That's what? 3. I know it goes 3 times. And then, so it goes 3 times. And now I need the what? Remainder. I'm going to write it right here. The remainder of the division, all you need to do is, on the calculator, what's going to be left over? Go 216 times 3. Which is what, 648. And then take that away from what, 855. That will be the remainder of the division. So 855 minus 648 is 207. That's the remainder of the division. Good so far. Now, once you figure out, if you're doing it this way, once you figure out what is the highest power of that base that we're dividing in there, then it's automatic from here on out. I know I'm going to divide what 6 what squared into here, and I'm going to keep doing this until I get down to 1's place. So I'm going to take 207 and divide that by what, 36. And it goes what, 5 times. That's perfect quotient. Then figure out the remainder. I'm going to get what, 36 times 5. I get what, 180. So 207, that's what I was originally dividing into, minus 180 is 27. So the remainder was 20 what? 7. All right. I'm going to divide this by 6 to the first, and just divide by what, 6. You get to a point you can do this in your head. Basically, 6 is going to divide into 27 what? 4 times. With 3 left over. Now, 3 divided by 1 is what? That's what I said, you get to 1's place like that. And so, how do I read it? Talk them. So I know that the 855 is 3543. All right, I did promise you a more efficient way, right? So let's look at that, but this is a method that will work every time. So I'm going to do the same one again. But do it a different way. Instead of figuring out what is the highest power of 6 that will go in there, I'm just gonna, I know I want to convert to base 6, I'm gonna start dividing by 6. That's it. See how this will work out. I'm not gonna be backwards from this essentially. And I'm gonna write it a little differently. Organize it. For here, I was putting down the quotient. Which ended up being what actual digits here. And then writing the remainders what here. Of the digits. I'm gonna do it just backwards or opposite of that. I'm gonna just divide 6 into here. I'm gonna write the quotient here, remainder here. All right, so I'm gonna go to my calculator and I'm gonna go say 55 divided by 6. I'm gonna do that 1 second. I gotta check on something here. Yeah, should be good. Forgot to bring my power cord. 655 divided by 6. 855 divided by 6. So it goes 142 times. Now, remember, so and once you start doing enough of these, you actually pick up on this pretty quick. You know it goes 142 times. I also know the remainder is 3. Now, remember what I said, the decimal part is the decimal form of a fraction, remainder over the divisor. We're dividing by 6. So if I have the denominator of 6, I would have to have 0.5, which is what, a half? 3 over what? That's how I can quickly know. Now, sometimes, you can't look at it and tell because, you've got so many decimal places there. But the remainder's got to be 3. Now, but every single time, when you want to figure out the remainder, I was dividing by 6. This was the quotient. So 142 times 6 is 852. Take that away from 855 and you get that what? Remainder of what? 3. Right. Now, we're going to just keep doing this. We're going to keep repeating this until I hit 0. And this is the only part that's a little squirrely sometimes for students, is this last part. So get there. Show you what I mean. Yeah, there it is. So I'm gonna keep repeating it. So now I'm going to get 142 divided by 6. 142 divided by 6 goes 23 times. Remainder we'll find by going 153 times 6 gives me 138. Take that away from 142. That's a remainder of 4. You do get to the point you don't need a calculator. 6 to go with 23. 3 times. With a remainder of 5. 6 times 3 is 18. Take that away from 23. 5. This is the part that is always the same, but it is a little squirrely when you first learn. When I go 6 into 3, that's smaller than that, right? So it goes 0 times. That's when you know this is done because you put that 0. And the remainder will be whatever this digit is right here. If I actually wrote it out, 6 goes into what? 3. Okay. 0 times, and 0 times 6 is 0. And my remainder has to be what? Less than what I'm dividing by, so it all works out. So this is how it will look at the end every time you do this. The same way. That will be your. All right, so we already know what the answer was here, right? How do you read this one? Bottom what? bottom up. 3543. Good. So this is a definitely more efficient way to do it. You don't have to figure out the highest power and so on and so forth, but either method will work. I definitely prefer this one. Now, when we haven't worked with base 2 yet, that is what, zeros and ones, that's all it is. Back in the 30s, when they were first doing, when computers were very first originated computing machines, and they were doing the coding of cards, they chose binary to do the coding because the 0 and 1 were switches, on and off. 0 for off, 1 for what, on. If you think about it, just visualizing, I know everyone's seen one before, a power switch. And it's got a what, 0 for what, off, and a what, 1 for on. So not today, but again, we will work with binary, not computer language yet. Anyone know what the computer language is called? Ever heard of it? It's called ASCII, which is an acronym for American Standard Code of Information Interchange. And basically what it is, every capital letter has 26 letters in the alphabet, every lowercase letter, every punctuation symbol is some 7-digit binary number, which means it has a base 10 word equivalent. Because of any nerds like me, Hitchhiker's Guide to the Galaxy.
42.
All right, I knew somebody would have it. 42. 42, if you've ever read, we saw the movie, they did a movie of the book, the first book, it's many books, but it was the first book, I don't know, what, 10 years ago or something, they did a movie. Does anybody even know what I'm talking about? I can tell you
haven't
what.
watched it, but I know what it is.
Okay, so the ultimate question of life, the universe, and everything. So if you ever read the book, they built a ginormous supercomputer that was designed solely to figure out what is the answer to life, the universe, and everything. And after millennia of computing, it came up with the answer of 42. So this is in the book. All right, so spoiler alert here. Asterisk symbol. Hashtag, right? Oh, no, hashtags now. That's what I'm trying to sign. But anyway, asterisk. You take, so it is a punctuation type symbol. And if you figure out what the decimal number is of this, and then convert it to a 7-digit binary number, so you take its 7-digit binary number, convert it to base 10, guess what it comes up to be? And if you do computer coding, the asterisk is what they call a wild card, where it translates as whatever you want it to be, literally. So it's the answer to life, the universe, and everything, whatever you want it to be. So, all right. I won't, you're going to be tested on that. Random facts, paper trivia tonight. Okay, so let's do some more of these conversions. So I'm going to give you a number of base 10, ask you to convert to another base. And let's see. Let's take 1,042. So that's base 10. You're going to convert to base 8. Give me its base 8 equivalent. All right. I've shown you two ways, trying to steer you to this way. A bit more than that, that's, again, sometimes, yeah, but either way will work. Yeah, it's the one thing that I make these up there.
What was the problem?
Okay, so you're gonna take 1,342 and convert it to base 8.
Okay, thanks.
You're welcome.
I was like,
Nope.
I was looking at that.
Oh,
I was
I
like,
think,
what the
where
heck
was
is
that?
that?
Yeah, I'm sorry, that's not some fun stuff. Those are our estimates. Sorry about that.
I haven't got it yet.
Okay. So far, so good.
Okay, I'm
All right.
confused.
Okay, no worries.
I got to like this.
Okay, so this will work. So right here.
Okay.
So now there's 8 times. And take that away from here.
Okay.
And that gives you, should be 6.
I was
And then we're
wondering-
gonna keep repeating it until we hit 0.
Okay. Let me see if I got it.
Yes. Okay. Yes, you do. Now, all we want to do now is. Okay, so there's in here. Now. Yes. So now, okay, yeah, it's fine. Then you hit 0. Okay, good stuff. So you go punch. 1,030. Okay. 167, 186. Now this goes into their 20. Now 20 times 8 is 160. So then there's 7. Now 8 goes into 20. No time. Okay. So. uh, If I want to get a base 8, take 8 into, 8 into, what am I to convert? 1,342. So when you punch this in your calculator, you're going to get 167 point whatever. So you know 167 is the quotient. Then I put a little arrow, and I'm going to write the remainder of this division. So go 167 times 8. When you do that on your calculator, you're going to get 1,336. Take that from 1,342. That's a remainder of 6. And now it's just repeat the process until I hit 0. That is 8 into 167. Now here you're going to get 20 point something or other. So it's 20 times. This one I can just mentally, just 8 times 20 is 160. Take that away from that. That says the remainder was what? 7. And then 8 goes into 20 twice. 8 times 2 is 16. Take it away from 20. 4. And here's where you know you win. When you're dividing into something smaller than what you're dividing by. 8 goes into 2. 0 times, the remainder will be 2. Then you read it bottom up. So you write 2, 4, 7, 6. And then they say, now the nice thing is on my math lab, when you punch in an answer that's in another base, they give you a field and they write this for you. So you don't have to actually type a subscript in there. All right, you got it? Okay. Now, what we haven't done yet is work with base 2. It works all the same. However, because it's just zeros and ones, it takes a lot, and the bigger the base, the less digits you need to represent a number. The smaller the base, the more digits you're going to need. Many, many years ago, I was at a conference. This is like the early 90s. And guy was doing math magic tricks. So I was like, oh, I gotta go see this. And he had these little coin purses. He had his little coin, you like push on, keep coins in them. I don't really see them around that much anymore, but he had 10 of them laid out on a table, numbered 1, 2, 3, 10. He said, to anyone out there, give me any dollar amount you want between 1 cent and $6. And so you might say $4.32. And just lightning fast. You say, he'd have to come up. I want you to dump out this one, this, and there might be 4 of the 10 coin purses. So don't mix the money. Just dump out the ones here, 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 and here, and then count it up. And it would come up to be $4.32. And immediately just because I'm a math nerd, I knew what he had done. And I thought it was genius. I'm like, oh, I can't wait I'm going to do this trick for my class. I did once, and I've never done it again. Not much of a show, so I don't have that magic flair. So there's that. And 1 and 2, I couldn't do the arithmetic that fast in my head. I even tried to have a calculator to do it. And of course, that was most of that right off the bat. What he did was in the first little coin purse, he put 1 penny. And the second, he put 2 pennies. And the third one, he put 4 pennies. And the next one, he put a nickel and 3 pennies. 8 cents, right? Next one, he had a nickel, a dime, and a penny, 16 cents. And I don't know what he used exactly the combination off the top of my head for the next one. But how much would be in that one, do you think? 32 cents, and the next one had 64 cents, and the next one after that had $1.28. Next one after that, $2 and something. He was going by powers of what? 2. So he literally had 1 cent. Then he had 2 cents. And then the third one, he had 4 cents. What? 8 cents. 16 cents, and so on and so forth. Now, remember I said, it might have been $5, maybe between 1 cent. I think it was between 1 cent and $5. 500 is not a power of 2. It was 88 cents in that last one, just to round it off to a round number. But there were 10 of them there. Way out. Anyway, I tried it. I used envelopes and had all the money in them right. But I remember asking him, how in the world could you do the arithmetic so quick? Know which ones? He said a lot of practice. So at that time I had 3 kids at home. So I didn't have time to sit and try to memorize that. And I said, when kids were out, I'll learn. I never did. But you literally, any number you can think of can be written as a sum of some powers of 2. And he just was able to do remarkably fast. So base 2 would obviously use powers of what? 2. So if I had a number like 1, 1, 0, 1, 0, 1, 1, 2, and say convert that to base 10. This is, and we've got many digits. That's why I always go 0, 1, 2, 3, 4, 5, and what? 6. So this would be 1 times 2 to the what? 6 plus 1 times 2 to the 5th plus 0 times 2 to the 4th plus 1 times 2 0 times 2 squared plus 1 times 2 to the first plus 1 times 2 to the 0. Now that's writing it out in its full glory expanded form. But if you think about it, I treat base 2 a little differently than any other base, simply because, and again, this got back to the idea of switches on and off. I have 2 digits, 0 or 1. Anything times 0 is 0. Anything times 1 is what? It's really just add up powers of 2. At the end of the day, I don't have to write it out, unless I'm asked to. But if I was just converting it, it's just add up, okay, 2 to the 6. That's what, 64? 32. But no, don't do anything with that. But then plus what? 8 plus them, nothing there. Then plus what? 2, and then plus what? 1. And that's what he was able to do. I mean, I can't even look at that and go, I mean, I could get it. I could sit there and add it up, but not as quick as that guy was. So it did make a very cool trick. I wasn't buying this whole, I practice and practice and practice. I think he was just one of those guys who could do arithmetic really quick. I have 107. 107. Okay. And if I'm converting from base 10 to base 2, I think of what combinations of powers of 2 I need. Because remember, every single base 10 number can be represented as a sum of powers of 2, some combination. So I just think about my powers of 2, and the ones I need, I put a 1 in that place value. The ones I don't need, I put a what? A 0. So I don't actually, when I do conversions with base 2, you can do this. But since it's just zeros and ones and the powers of two, that's, I treat it a little different. Okay, any questions? All right. Well, let's figure out,
Will base two numbers always be 7 digits?
no, it could be as many digits as you want. I mean, because if I, like here, 7, I just picked 7 digits because I asked you, but you could have 8 digits, just as your next place value, be 2 to 7, 128, and so on and so forth. I start with this, doing this, because this is probably some of the more difficult stuff to do. And I want to just have time to work on. And when we talk about historical numeration, which we will go back and touch on some historical numeration. This is an evolution to get to this positional place value system that we use today. Once upon a time, we, like the ancient Egyptians, just used what was called simple grouping. They had symbols that represented power of 10. And if you wanted, so in using their simple, the ancient Egyptian numeration system, if you wanted to represent a number like 1,352, you would have whatever symbol that was 10 cubed, you would write one of them. And then whatever symbol was 10 squared, you'd have to write 3 of them. And then whatever symbol was for 10 to the first. So there was a finite number that, that is, there was a largest number that you could write because for each power of 10, they would have a symbol. So there was a stopping point at some point. And they didn't have the number 0. The concept of 0 was not there, nor did they have negative. And then we moved to what's called a multiplicative grouping system. And that required 2 symbols only. You would have your basically kind of your face value and then a power of 10. And so instead of having, the jump was instead of having to have 4 symbols for that 10 to the first, you would have the symbol for 4 and then 1 symbol for 10 to the first. So every digit would have to be represented with what, 2 symbols. This is more of a Chinese system. So, however, once this came together, this positional place value system we have, then there is no upper limit. You can larger and larger and larger and larger and larger numbers. Okay, so on the homework on my math lab, it is you're not going to be responsible for, because I did not cover everything yet. All I really want you guys to work on between now and Wednesday is converting from some base to base 10, and then from base 10 to what some base. I never remember what the cut is here. So let's go figure that out. All right, so we're going to be working with 4.4. An idea what we're going to be looking at. Now, so this first problem lists the first 20 counting numbers in the indicated base below. We're like, we didn't do anything like that. Well, we did. We talked it. We haven't really wrote it down per se. So here's the textbook. So what they've done here is they wrote out counting numbers and 0 starting with 0 in both base 10 and base 5. Look at the pattern. Base 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 blah. I mean, that. Look at base 5. 0, 1, 2, 3, 4. And then what? 1, 0, 1, 1, up to what? 1, 4. And then it what? Kind of like you said at the very get-go here, once you hit your last digit, then you what? Bump to the next what? Place value. And that's how it works. So If you could put a base 6 in here, it would go 0 through 5, and then you hit what, 1, what? And really what it is, and like this one, when you get to 4, you're out of digits. You gotta go to the place value, what, 5 the first. One group of 5 the first, and 0, 5 the 0 place, and then 2, and so on and so forth. So when you look at this problem here, this is an indicator, this is base 5. So you're gonna type them in, you're not gonna have to put the subscript. You'll just write 0, 1, 2, 3, what, 4. Then go what, 1, 0, 1, 1, up to 1, 4. Biggest thing is make sure you count that you only put what, 20 of them in there. And remember, you're starting with 0. So I've had students get frustrated on this one because they had 21 numbers in there, or they had 19 only, and it's looking for 20 of them. All right. So there's a few others like that. And here's our asking you to write it out in what, expanded form? Base 2 stuff. Martin says goes up to about. Here you're going to, when it says go from decimal form to the given base, that's base 10. In this case, to base 16. So remember when you work base 16, write out 0 through 9, A through what, F, and then go A is 10, B is 11. So that when you are doing this kind of conversion, if you're going to base 16, and you have to find these remainders, you might find a remainder of 11 or a remainder of what, 12, in which case it's 12, let's see. All right. Yes. Never saw that before. Okay, so there's initial. I don't even remember it right. All right, so you can see there's 31 problems here. You're only responsible up to 20. Past that, so down. Homework. Is what did I just say? 1.4. Work problems 1 through 20. And then when we come back on Wednesday, we will finish out the rest of this section. Probably that would be it. But all right, guys. Thanks for coming in. If you need a mathematician name, we can take care of that here today. All right. Oh my gosh. Okay, so Maddie, we're done for the day. Did you get the homework okay?
Yep, I got it.
All right. We will see you on Wednesday.